Hello, today we will talk about Le Chatelier's principle. It states that if a chemical reaction is at equilibrium and it experiences a change in pressure or temperature or concentration of products or reactants, the equilibrium of that system will shift in the opposite direction to offset the change. Le Chatelier's principle basically describes the fact that a reaction at equilibrium does not that easily give up on it. Even if we try to throw it off, the equilibrium would shift but reestablish itself. Let's consider this reaction. Nitrogen reacts with hydrogen to produce ammonia. It is a reversible process, and given that the system is closed, there would be an equilibrium reached between forward and reverse reactions. Inside of this tank, we have hydrogen, nitrogen, and ammonia. Their concentrations are constant over time as a result of the dynamic equilibrium between forward and reverse reactions. Now, let's say we want more ammonia to be produced. To get it, we may pump into the tank more nitrogen and hydrogen. Increase in concentration of the reactants will surely make the forward reaction to go faster. More collisions, faster rate of reaction. And maybe for a short period of time it will look like we have succeeded. There will be more ammonia produced. But the more ammonia we have, the faster the reverse reaction will be happening. Soon enough, the speed of the reverse reaction will catch up with the speed of the forward reaction and the equilibrium will re-establish itself. There will be some shift in the concentration of reactants and products, but once again, the concentrations will remain constant over time. Let's look at graphical representation of shifts in equilibrium. From this moment in time to this one, there used to be equilibrium. Then at this moment, we've pumped inside of the tank a considerable amount of ammonia. Here's the spike in the concentration of ammonia. So the reverse reaction of decomposition sped up, increasing the concentration of nitrogen and hydrogen. And on the graph, we see the decrease in the concentration of ammonia while there is an increase in the concentration of hydrogen and nitrogen. And here and forward, the new equilibrium is established. Concentration of reactants and products once again remain constant over time. Please notice that the initial increase in the concentration of ammonia, the product, leads to increase in the concentration of nitrogen and hydrogen, the reactants. So we say that equilibrium shifted to the left. We can say equilibrium shifted towards reactants. This is what Le Chatelier's principle is all about. The equilibrium shifts in the opposite direction to offset the change. The equilibrium is kind of fighting us, doing the opposite of what we've done to it. We've increased the concentration of the product. The equilibrium answered us by increasing the concentration of reactants. Here is an example of the same reaction, where concentration of nitrogen was drastically increased. Increase in concentration of even one of the reactants will lead to more collisions of reacting substances and increase in speed of the forward reaction. So we see a decrease in the amount of nitrogen and hydrogen as they react and turn themselves into ammonia. Concentration of ammonia goes up and a new equilibrium is established. Here we increase the left side of the reaction. Equilibrium shifted into having more ammonia. Once again, it is fighting us. It offsets the change that we've inflicted on it. We say that equilibrium shifted to the right, or equilibrium shifted towards the products. Here's another graph of a process at equilibrium. A gas, phosgene, decomposes into chlorine and carbon monoxide. In this moment in time, we managed to pull a lot of carbon monoxide out of the system, decreasing the concentration of the product. We've affected the right part of the equation. The equilibrium will try to compensate for it by producing faster what we've taken away. It will speed up the production of chlorine and carbon monoxide, shifting equilibrium to the right. Let's talk about the effect of pressure. Change in pressure has little or no effect on equilibrium of liquids and solids, but it does affect gases. Over here, we have a system with nitrogen, hydrogen, and ammonia at equilibrium. Let's say we push the piston down, applying more pressure on the system. We are squeezing the same amount of molecules into the smaller space. The pressure of the gases would increase. But these are reactive gases. Instead of being all squeezed up, they can react, forming more ammonia molecules, thus decreasing the number of molecules and consequently decreasing the pressure. So once again, Le Chatelier's principle. We've increased the pressure, the gases reacted in a way that decreased the pressure. The equilibrium shifts to the right, or equilibrium shifts toward the product. We have 4 moles of molecules on the left side of this equation and only 2 moles on the right. So this equilibrium under pressure will shift towards a smaller number of moles of molecules, as they will produce less pressure, compensating the disturbance that we've created. If, on the contrary, we would decrease the pressure of gases in the system by pulling the piston out, the equilibrium would compensate for this decrease in pressure by shifting to the left and producing more moles of gases. More nitrogen and hydrogen would be formed. Okay, let's count moles of gases in this equation. 1 mole on the left and 2 moles on the right. If we increase the pressure of this system, where would the equilibrium shift? Please answer this question to yourself. Okay, check yourself. Equilibrium will shift to the left. And if we decrease the pressure, the equilibrium will shift to the right to fight us and to compensate for the decrease of pressure we've created. It will increase the pressure with the higher number of molecules. And in this reaction, the gas on the left is a colorless gas, while gas on the right is of reddish brown color. When 2 of these gases are observed together, the intensity of the color might vary. One of the things that might be in control of the color is the amount of pressure in the system. If we increase pressure, the equilibrium will shift towards forming more of the dinitrogen tetroxide because this shift will lead to a smaller number of molecules and alleviate some of the disturbance, some of the pressure that we've created. While if we decrease the amount of pressure, the combination of these 2 gases will turn more dark and brown because equilibrium will shift to the right and more of brine nitrogen dioxide will be formed. Okay, more examples. I know, you might be rolling your eyes and whining not again and all, but here is a trick question for you. Where equilibrium will shift in this equation if I apply pressure on the system? Pause the video and answer this question to yourself. The answer is that pressure is not going to affect equilibrium in this case. We have an equal number of moles of gases on both sides of the equation, 2 moles on the left and 2 moles on the right. So while an increase in pressure will speed up forward and reverse reactions, it will speed them up in equal measure. So there will be no shift in equilibrium. Okay, last example regarding the effects of pressure. In this equation over here, where will the equilibrium shift if we increase the pressure of the system? Pause the video and answer this question to yourself. The equilibrium will shift to the left. In case of the increased pressure, the equilibrium will shift to the smaller number of molecules. If we decrease the pressure of the system, then equilibrium will shift towards the product of the reaction, increasing the concentration of carbon monoxide and oxygen. Time to talk about the effect of temperature on the equilibrium. Here is the old friend, reaction of synthesis of ammonia. It is an exothermic process. I know that because heat of reaction is a negative number, and I know this number because I know how to use table I in the reference tables. And so should you. With the understanding that synthesis of ammonia is an exothermic process, I will add heat to the right side of the equation because it is energy released as ammonia is formed. Now, I will treat heat as part of the reaction, one of the products. If I heat up my system by heating up the tank with these gases, I'm increasing the amount of heat. The equilibrium will try to compensate for this disturbance by quickly running the endothermic reaction of ammonia decomposition. This reaction will absorb some of the heat and will compensate to a degree the damage that I was trying to inflict on it. The equilibrium will shift to the left. If, on the contrary, I will cool down my system, stealing energy from it, I might do it by putting a lot of ice outside of the tank. The system will try to compensate by increasing the speed of the exothermic forward reaction of synthesis, and the equilibrium will shift to the right. Let's look at the example of endothermic reaction. Heat of reaction is positive, so the synthesis of hydrogen iodide is an endothermic process. Heat will be absorbed in the process, so I should add heat to the reactants part of the equation on the left. Please remember that the reverse reaction of hydrogen iodide decomposition would be the exothermic process. So, if I will heat up my system, that means that I will be increasing the amount of heat. And since the heat is part of the reactants, the equilibrium will shift to the right, absorbing all of this heat in the endothermic process of synthesis. If I will cool down the system, it will be the equivalent of stealing heat, making it smaller. The exothermic reaction of hydrogen iodide decomposition will run faster to compensate for it, shifting equilibrium to the left, thus increasing the concentration of reactants. One more example of the effect of temperature on the equilibrium. Pause the video and decipher this reaction in the graph. Okay, decomposition of carbon dioxide is the endothermic process. After the initial equilibrium was established, the system cooled down somewhere around this time. Decrease in temperature means decrease of energy, decrease on the left side of the equation. Exothermic reverse reaction will speed up to compensate for the loss of energy, shifting equilibrium to the left. We can see the concentration of carbon dioxide increases as the concentration oxygen and carbon monoxide goes down on the new equilibrium. The last and the simplest of them all, the effect of the catalyst on the equilibrium. Catalysts are the substances that increase the speed of the reaction by decreasing the amount of activation energy. The simple fact is that when a catalyst does that, it increases in equal measure the speed of the forward as well as the reverse reactions. Since both of the reactions speed up, equilibrium does not shift, and we do not see any changes in the concentration of reactants and products of the system.